In this video, we're going to introduce another gate, which is the exclusive OR gate. And we have a counterpart to that gate. Similarly, like we had with the AND gate and the OR gate, we have the exclusive XNor gate. So the exclusive OR gate looks similar to an OR gate, except we have this extra little line here. And then for the exclusive XNor gate, we have what looks like the exclusive OR gate with the little circle on the output. And we know what the inputs and outputs are for the NAND gate and the NOR gate, as we talked about in the last video. But now we're going to define the outputs for the exclusive OR gate and the exclusive NOR gate. Now the exclusive OR gate operates on the basis of the output being high only when one of the inputs is high, which is similar to the OR gate, except this case where X and Y are both high, we get a 0 for the exclusive OR gate. And then the exclusive NOR gate is just the inverted exclusive OR gate. So we can take our exclusive OR gate and represent it in a sum of min terms. And conversely, we can represent it as a product of max terms by capital M naught and capital M3. And then we can take a similar process for the exclusive NOR gate to arrive at the sum of min term and product of max terms. So for the exclusive OR and the exclusive NOR gate, we don't get kind of a nice function to represent them in the Boolean algebra that we know. But we can introduce a new operator, which is the exclusive OR operator. That's a plus with a circle around it. And that's how we can represent the exclusive OR gate. We have X, and then the exclusive OR plus sign, and then Y, which are the inputs. Now the exclusive OR operator follows the rules where when you have X and 0, you simply get the X input. When you have X and a 1, you get the opposite of the X input. And when you have X exclusively ORed with itself, you get a 0. Now we can represent the exclusive NOR gate simply by the exclusive OR equation, and then put that bar over the top to symbolize the inverse. And one rule to take note of, as it becomes very important, is for multiple input exclusive OR gates, the output is 1 if an odd number of inputs are also 1. So if we have something like a 3 input exclusive OR gate, call this X, Y, and Z, the output would be 1 if X is equal to 1 and Y and Z are equal to 0. But if X and Y are equal to 1 and Z is equal to 0, the output is 0. But if all 3 are equal to 1, then the output is also equal to 1, which seems to be the opposite of the 2-input exclusive OR gate, where if both the inputs were high, the output was 0. But again, we're paying attention to the odd number of inputs that are connected to this exclusive OR gate. So now we can look at the mastery problem, and this is going to be a combination of all the things we've learned so far. So we have a 4-input truth table, W, X, Y, and Z, where we have 16 individual combinations, and we're given what that truth table is. So we want to find F as the sum of min terms and the product of max terms. And then after that, we want to design a circuit to implement this function F. So we can start with the first part where we are going to express F as a sum of min terms. And from this, we can simply express F as the following. And then we can also express that as a product of max terms. So you could also express this as something like 0, 3, 5, 6, 9, 10, 12, and 15. And as long as you have this summation sign here, the message is clearly sent. And the question for part 2 is, how do we design a circuit to implement this? So we see again that we have 4 inputs and we have a lot of different sums for the midterms, which means we're probably going to have a pretty big circuit. And what you could do is draw out your circuit like this, where you express all your terms. So 0 is W bar, X bar, Y bar, Z bar, and go all the way down the list such that you get all your terms. So you would have 8 AND gates summed all together with one OR gate that has 8 inputs. And while this looks very complex, there is a way to simplify this. And first we're going to divide this truth table into sections of 4 just to make it easier to read. So looking at this truth table, you can see that you get a 1, and we have W equals 0 and X equals 0. There's not much commonality between the Y and the Z. For the second block, when you have W equals 0 and X equals 1, again, that's when you get your outputs to be high. Then for the third case, when W equals 1 and X equals 0, that's when you get your outputs to be high. And for the last case, when W equals 1 and X equals 1, that's when you get your outputs to also be high. And this is where you might start drawing a blank as to how to simplify this circuit and what's the catch. Well, maybe it's not anything special with Y or Z. Maybe it's something special about everything together. So let's consider all of the inputs. And for this last combination, you have 2 inputs are high or 1. Okay, but then here we have 0 inputs are high. So if we go down to the second block and we start to see that if we have 2 inputs here or 2 inputs here, then we have a high signal. And let's see what's going on in the third block. So if we look when the output is high, again we have the condition of 2 inputs being high. So we're starting to notice a pattern, and let's see if that is confirmed in the last block. Here's our 2 inputs, they're high, but this first one we have 2 inputs high, and this last one we have 4 inputs high. In all of these blocks, we have 2 inputs being high. In the first block, we have 0 inputs being high. And in the last block, we have 4 inputs being high. So you can notice the trend that an even amount of inputs are high. Okay, so we found a trend. And how can we relate this to what we've learned? Well, if we scroll back up here, for a multiple input exclusive OR gate, F is high if the number of inputs that are also high are odd. But that's not the case we have, because the case we have is if we have an even number of inputs that are in a high state, the output is high. So kind of the opposite of what's going on here. Well, what's the opposite of an exclusive OR gate? We look at the first thing we talked about in this video. The opposite of an exclusive OR gate is an exclusive NOR gate. And that's the key to this problem, is all of this from the truth table can simply be represented by this huge combination of gates, which is perfectly okay to do. But you can also express this as an exclusive NOR gate with W, X, Y, and Z as the inputs. And while these gates are the same thing, and they do get you the same result, this one is a lot easier to read.